Alrighty, guys. We've got another fun and exciting class coming your direction, all the way from Hattiesburg, Mississippi. It's GHY 326 Introduction to Meteorology and Severe Weather Forecasting. I'm going to be your professor. I'm trying to spice these things up the best I can. I understand that these aren't probably as much fun as showing up to class. But I hope everyone is doing what you can, doing the best with what you got to make the best of the situation as best as you can. I hope you guys have been keeping up with the notes and the lectures that I've been kicking out to you guys. Again, if you have questions, as always, send them my direction, and I'll be happy to answer them for you and try and walk you guys through exactly what we're looking at. If there are enough questions between now and the final, as you guys start looking stuff over, what we'll do is I may just make another lecture with a kind of a review or going over some stuff. I'll be honest, I haven't quite decided yet how everything's going to shake out. I don't have a solid feel for it, but I am understanding. At least that's what I'm trying to be. I know that this is kind of weird, and so, or at least not what you signed up for. So I'm trying to be respectful of that as we kind of wind down class and get ourselves toward the final. So, this is going to be probably one of the last, straightforward lectures, and what we're going to do after this point is kind of transition to kind of a quasi, what would have been in-class assignment stuff, but it's going to be at-home class assignment stuff, and we'll probably kind of figure that out piece by piece as we kind of go along. I wish I had a better feel for what it is you guys are about to get into, but I'm still trying to nail down exactly how this is going to look. But I will say, as we go through time, that there will still be assignments, but what I may do is I may weight them a little differently, not in your overall grade, but instead of doing, since we had up to 4 more forecasting assignments to go, I may just make it 2 or 3 and then make 1 of those or 2 of those worth double points. So you're not going to lose out on an opportunity to gain those points, but there just may be less work for you guys to do. Having to transition this to online, a lot of you guys just basically lose, unfortunately, some of the cool stuff and the camaraderie and the teamwork of working together and everything that comes along with putting together a forecast. So in an effort to make things a little bit easier on you guys, I've decided that as we kind of work through things, we may have to make some changes. Not to the syllabus, not to your grades, but just how we attack getting to that point where you get to drop your lowest midterm for the average of all of your forecasting assignments, and getting to a point where we have enough forecasting assignments to the point where that average is actually worth something to you. So we'll get there. In the meantime, like I said, this is probably the last straightforward lecture that we're going to have. There will still probably be a video here and there. But this is probably the last, hey, I built this lecture. This was what was going to be in class that was then kind of tailored for online. The rest of everything I'll kind of wing because it would have been stuff that would have come up in class during in-class discussions and in-class forecasting assignments. Okay. So building your weather forecast. That's what we're going to be doing. It's going to be fun. Now, last lecture we went through putting together that quick forecast. The previous lecture we talked about weather forecasting itself and put together a forecast. What I'm trying to do is I'm trying to give you guys the experience of watching somebody and allowing you to also take notes while working through your own forecast because pretty soon I'm just going to drop you into the deep end of the pool, and I want to give you as many examples as possible for you to refer back to when it is that you're putting together your forecasting assignment. So, three big hitters that I'm going to knock on here for you guys as you go into making your forecasting assignments. It's important to look at the days leading up to a forecast to gain an accurate representation of your potential atmosphere. Snow won't stick to the ground when the ground is 75 degrees, and the ground is going to be 75 if the previous handful of days were in the 80s. Flooding may not occur, may not occur, if it hasn't rained somewhere for a week. You never know. If you get a lot of rain all at once, well, sure, you're still going to get flash flooding. But the idea is that if it's been dry, if the antecedent conditions, as we say, are dry, then it's going to take more water to get widespread flooding. Looking at the entire atmosphere can give you explanation as to why models are suggesting certain surface conditions too. So an 850 millibar temperature of 5 degrees C is a good indication that it's not going to be in the 90s at the surface. Even if you get some crazy super adiabatic line, chances are you're not going to end up with temperatures in the 90s if your temperature was at 5 degrees C at 850 millibars. And then the last one that I'm going to say on here is, as the wind blows, the temperature goes. That was wise words handed down to me by my chief meteorologist in Amarillo when I worked down there. And it totally holds true. South wind, warm wind. North wind, cold wind. East wind, I don't know. West wind, I don't know. You gotta, depends on your specific locale. If you're up against the Rockies, a west wind is going to be a downslope. That's going to be a warm wind. If you're living on the east coast of Florida, an east wind is going to be a warm wind because it's coming off of the tropical Atlantic or subtropical Atlantic. Location. All right. So, what we're going to do is we're going to look at 4 random SKUTs that are poked out in the middle. Not supposed to be there. Hey, we're going to do some live slide updating. How about that? Yeah, that's what we're going to do. All right. So, we're going to move that up there. All right. So, it's important. I could start this over, but I'm not going to. It's important to recognize important data, too. Okay, so we're recognizing trends, and we got to recognize some important data. I'm really not sure why those are up there. I don't know how they ended up where they ended up. Here's your checklist that we went through, and you're still going to go through this as you head through all of your assignments. Save maybe that last assignment. I might be nice in the last assignment and not make you guys go through all of this. But it's important to go through and fill this out because, as I said in the last lecture, I still have my forecast sheet here. I go through all of this stuff too. You guys aren't the only ones. I'm not just making you do busy work. It's actually important for figuring out exactly what the weather is going to be doing. Especially in as specific a detail as I am asking you guys. There's also other important stuff. You got to cross-examine the data, as I mentioned earlier in class, which is, do you have divergence happening in the same place you have warm air advection? Are you changing your wind speed with height? Is there vorticity and vertical velocity happening in the same place? Do you have a dew point spread that's different at different levels? Is there some vertical motion above an area where we're pulling in warm, moist air? So all of these things, I call it cross-examining the data, but really all it is instead of going wrist deep, you're going elbow deep into the data. And this is, again, stuff that I do every single time that I put together a forecast. All right, so what we're going to do is a quick Memphis cast, and this is where these SKUTs come in. And what I'm going to do is I'm actually going to make these a little bit smaller so that we can actually see. And it may be kind of tough to make out depending on how small and tiny you're watching this on your screen. If you've got some big screen TV you can watch this on, you may not necessarily want to see my face this big or see the outside this big on some big screen. But I will say that it would help you see some of these numbers maybe a little bit easier. Okay. So we're going to start things out at 12Z on the 4th of April, 312 hours out. and we're just going to watch things moisten up. We're just watching things. Oh, that's right. That's why. Okay, hold on. Just kidding. We're not moistening yet. Okay, so this is the point I was making. Antecedent conditions. Antecedent conditions. Antecedent conditions. That's right. Okay. So this is why these were here. So I thought that these were the ones down lower. They're not. Okay. Bear with me here. Again, this isn't bad. This is what? The fifth or sixth lecture I've done, and this is the first goof I've had. I'm actually really proud of myself because you guys know from class that generally I goof at least once during class. Okay, so recognizing important data. Antecedent conditions, super important. You got to know trends. The trend is, you can see on the skew T here, this is just looking at the skew T, that we're going from a couple of high clouds in here to maybe a couple of extra clouds. And in the morning here, you can see that we're 52 over 50 down to the surface on April 5th at 12Z. Maybe a little bit of fog out there. Notice on your wind here, in fact, here, hold on a second. On your wind here, we've got a southeast wind, and then that southeast wind it kind of flips back around, and then it continues to be southeast. But look at the aloft. We've went from northwest back to northeast, back to southwest, and now fully southwest. You can kind of see the difference in your wind direction and intensity. You're going from a wind at 850 millibars out of the south-southwest at about 10 knots to out of the southwest at about 35 knots. And you can see that in the hodograph up here as well. Watch the hodograph grow in size. Boom. Boom. See how it gets bigger? Here, I'll kind of circle all of these, and then I'm going to make a bigger circle out here. And you can see how the exaggeration within the hodograph is directly linked to that exaggeration in the wind field. I didn't really have much of a wind field here at 5, 10, 15 knots. And then now we're talking 30, 40, 45, and 50 knots. And you can kind of see that there's a possible has type down here, none. And we've got some high clouds, but that's it. We're nice and dry closer to the surface. Then all of a sudden we're moist all the way through. We've got some instability. We've got a bunch of helicity and shear. And now our possible has type is there because, well, everything is basically lining up at this point to get severe weather. Now, this was the 384-hour GFS for April 7th at 12Z, so that's 7 o'clock in the morning. And this is old data, too. This is from March 22nd. So this is old data. But it paints a good picture. By the way, since it is not April 7th yet, as of this recording, we'll have to see if this holds true. We'll see. I don't know. Yeah. This would be a big win for the GFS at 15, 16 days out if it got it, but it's not got it. All right, now let's do the quick Memphis cast. What we're going to do here is I'm going to give we're going to build a forecast here with a limited amount of data. And the goal is here to show you guys that even with a limited amount of data, I think you guys can still put together a decent forecast. Then, when you guys are gifted all this extra data that you have to look at, I tend to think that putting together your forecast is going to go pretty swimmingly for you. Okay, so here we go. Memphis Castaway, 500 millibars. We're watching, well, it looks like a trough here. Trough here. Come on, trough me. Trough here. Trough there. Trough everywhere. Dropping to the south and southeast. Now it's here. Now it's here. And now it's there. So it kind of goes southeast and then kind of takes off to the south. And we can go back up and go back down. You can kind of see it just kind of traverse from the Pacific Northwest and kind of open up out into the plains. All right. So what do we know? Basically, just by looking at this, what do we know? What can we figure out? What can we talk about just from seeing a trough dive from basically Washington and Oregon into parts of Nevada, into Arizona, and then out and into parts of Oklahoma, Texas, and Kansas. All right. So we know that this trough comes down from the Pacific Northwest. We also know that the pressure gradient at 500 millibars tightens up as it approaches our forecast point. Because again, we are talking about Memphis, and if you don't know where Memphis is, we're talking about right here. So we're kind of a west-northwesterly flow. We're going over the top of a ridge. Now we've turned back kind of west-southwesterly, starting to see some divergence, and now we're southwesterly. with some divergence. All right. There's the pressure gradient tightens. Okay, so sweet. So what have we learned? Okay, so as the trough approaches, the divergence is going to allow for lift, and that lift is going to be synoptic scale lift. The low-level response ahead of a trough is a southerly flow. Now, we learned this in previous lectures, so we can then infer from that cloud cover is going to increase in the days leading up to March 28th, which is our day that we're concerned about here. March 28th at 18Z is when we're trying to figure out what. There we go, up there. That's the day that we're looking at and trying to give a forecast. You see, we go back in time to the 25th, 26th, 27th, 28th. All right. So cloud cover is going to increase as we lead up to March 28th. Your temperature is probably going to increase in the days leading up to March 28th because we have that return southerly flow based on where that trough is approaching. And the humidity is probably going to increase too because the southerly wind, as the wind blows, the temperature goes. With it comes the humidity because it's coming off of the Gulf of Mexico. So what we can kind of infer from this beyond that is on March 25th, it's going to probably be a mostly sunny day. We've got convergence with that kind of westerly and northwesterly flow. On March 26th, that's the peak of the ridge. So clouds may start to increase, or it may still be mostly sunny. We don't know that yet. We haven't looked at more information. We're just, again, this is stuff that we can pull basically straight from here. We had a west-northwesterly flow, a little bit of convergence. We're probably still sunny. Now we're at the top of the ridge here. We may see some indications of downstream divergence from that trough opening up across parts of the Intermountain West. Because of that, we can't rule out the possibility for maybe some high cloud cover. By the time we get a little bit closer, then we talk about more clouds and more clouds. Okay, so by the time we get to the 27th, now we're underneath kind of that west-southwesterly flow. We're just off to the east of the trough. The trough is to the west. Divergence has started to occur. Mid and high-level clouds are likely. We're starting to get into more of that synoptic scale lift. And then by March 28th, that's this day here, we're talking about being underneath that southwest flow. We're near the trough. Clouds are then likely. Now we're dealing with something. It's a different lift. It's mesoscale lift. Remember the three kinds of lift we talked about: synoptic, mesoscale, and microscale, right along that front. And so now we're mesoscale lift, and precipitation is going to be possible given the right ingredients. So let's see here. Let me fix the old video up here. It looks like I've frozen for a hot second. There we go, and I'm back. So we've figured all that out, and we haven't done anything but look at the 500 millibar wind chart, and we've just grabbed basically stuff that we've learned through the course. It's stuff that you guys, if you were listening to me say that, and you're like, how the heck did he figure that out? It's all in your notes. I'm not joking. It's all in there. We haven't done anything but infer mass balance, in essence, and divergence with all of this, as well as the low-level response, which is based off the fact that areas of low pressure spin counterclockwise. So they're pulling up stuff from the south. So this is all stuff that you should be able to figure out. And this is why during this class I'm big on thinking outside the box. There isn't always just one question, one answer. You got to kind of open up your mind and pick different things from different places to be able to kind of pull out the information that can help you get to a final answer. All right. We're gonna take. I'm gonna leave you guys with a darkening sky outside, and we're gonna take a break for a second. I'm gonna leave you guys 5 seconds to grab a quick drink or something. What is it? We've been going for about 15-20 minutes. I said about every 10 to 15 I'd give you a break, so I apologize. But I'll let you guys take a break real quick. While I take a swig as well. Again, more water. I'm really proud of myself. Yeah, hopefully you guys had an opportunity to take a break. I'm going to shrink myself back into the corner, and we'll get back down to business here. Let's see if I can. We'll get back down. Let's slide that over. There we go. I want to make sure you guys can see all of the information on these slides. All right. So again, like I was saying, we haven't done anything extra. I'm not using any extra information or smarts or experience or anything to figure out what we can infer from this. This is all stuff we went over in class. It's all about remembering what that stuff is and then applying it. That's all this stuff is. Looking back in your notes and applying, trying to remember these things and applying. So that's what we figured out. Now we can go from here and let's click into the data. Let's see how right we were. Right? And I did this, by the way. I wrote this all up in real time. This isn't me cheating and, I had access to the data, so I know these things are coming. I don't. Or I didn't at the time. Now I do because I put the slides together. But at the time, I was like, okay, well, let's look at the data. And I tried to do this as straightforward as possible and not to use any extra information that you guys wouldn't have access to. Okay, so here we go on the 25th. Okay, the 25th we said should be mostly sunny. Under a northwest flow, and we should have some convergence. Okay, so we'll come down here. Is our flow out of the northwest here? Oh, come on. Is our flow out of the northwest here? I would say that it is. Our hodograph also says we've got a northwest flow. Because remember, the hodograph, you stand in the center here, and then you're looking out and following the line, and at each point, that's the wind speed and direction. So you're off to the northwest. So we've got a northwest flow. So we should be dry and mostly sunny. Well, how about that? We're nice and dry. We should be mostly sunny. In this case, we're pushing 70 degrees. That's just as an aside. Okay. So there we go. So that's the 25th. Well, what about the 26th? Now we're at the peak of the ridge. So we may start to see extra clouds. We don't know how much of the downstream divergence we're going to be a part of or not. So let's check. Well, probably not. I mean, you may be able to make the argument that you've got enough cloud cover in here, but you can already start to see that we're westerly at top of the ridge, but the response, now that the area of low pressure is starting to approach from the west, the low-level response is actually pulling in wind from the south and southwest. This is also due to the fact that that ridge of high pressure, let me clear this out, that the ridge of high pressure, right, so we are now, so originally we were here, now we're here, your ridge is here. So there's your ridge of high pressure. I got a bug in here, you gotta be kidding me. And so your wind is gonna be going around like that ridge of high pressure. So now at the surface, we've got kind of a southerly and southwesterly wind. Hey, look at that, there you go. Temperature is warmer at 77 degrees. And again, that makes sense. We go back to here. We said that the temperature would start to increase in the days leading up to March 28th because we were talking about the low-level response ahead of a trough. And we could probably also say on the backside of a ridge is a southerly flow. So the cloud cover has already started to increase and the temperature has already started to increase. So now we go another day into the future. And you'll notice that we can go back up and back out. We haven't really done much in terms of moistening the column up. You could make the argument that you've increased the cloud cover on the edges here. You've got more cloud cover down at the surface. You've got some extra cloud cover aloft. But truly, you haven't done a lot for cloud cover. Maybe a little bit. We now have wind coming back around and out of the southwest because again we've made it over the ridge and we're now in kind of that west-southwesterly flow. We're now starting to talk about having some parameters down here that matter. We are possible has type severe, but there's a piece of information on here. There's a piece of information on here that we talked about originally a couple weeks ago. This is before spring break. You dig back through your notes. I said that if we don't get one thing, if there isn't one number that's higher than another number, we're not getting anything. You guys remember what that is? It's down here. Right in here. That may be tough for some of you guys to see. But what that is that's the max temperature and the convective temperature. And what you have is the max temperature is nowhere near high enough to get convection. Convective temperature is 91 degrees, max temperature is 81. So it is unlikely that we are going to get convection on this day, even though we have maybe some extra cloud cover. So we can go back up and we can say, okay, so what do we say? Southwest flow, divergence occurring, mid and high level clouds, likely, and we're dealing with synoptic scale lift. Okay, well, some mid, yeah, that's more lower level clouds, and some high level clouds, okay. And then, yeah, that flow is in there too. All right, so now we can go one more day into the future. Well, now this looks a little more like something that we would care about, right? So now we are good and moist most of the way through the column. Our hodograph is showing not a sickle shape or anything, but the hodograph is showing a southerly turning southwesterly, turning west-southwesterly as you move up in height. Our possible HAZ type here is a marginal Tor, and we've got a whole boatload of stuff down here to keep tabs on. And what do we say? Southwest flow, we're near the trough clouds, likely mesoscale lift, precipitation possible underneath the right ingredients. Yeah, I'd say we got cloud cover. I'd say we have that southwesterly flow. I would say that precipitation is possible given the right ingredients, and we've got some omega inside of our effective inflow layer in an area that's pretty moist, where we've got turning with height. We can see that up here. We've got all of these parameters down here, and that also leads to that. So, how about that? I would say, yeah. I think we covered our bases. I think we did actually a pretty good job. We may have missed out here, instead of mid clouds, maybe low clouds, but I think the inferences that we made based on just the 500 millibar wind map, that is all we looked at, we were able to pull out of the data a lot of stuff. And this is all stuff that we went over in class. It's just divergence causes lift, wind flows around low pressure counterclockwise, and a trough is an area of low pressure. We've got wind from the south is warmer, air from the Gulf of Mexico is more humid, wind is deflected to the right of the surface due to friction, okay. Warm air rises, rising air cools and condenses and forms clouds, and repeating warm air rising with humidity in the same area eventually creates precipitation. That's all we've done, and we were able to create a forecast off of the available data that we had. Now, it is a pretty rudimentary forecast. It doesn't offer a lot of specifics, but it's a forecast nonetheless. And a meaningful forecast as well for some people. If you're somebody that says, oh, I've got yard work to do on March 28th, well, does the temperature matter really, or is it just matter that you have an opportunity to, do it the day before it actually rains? All right, so now what we can do is we can cross-examine our data. Notice, I'm not going to go through the whole checklist that's up here. I'm not going to do the whole thing. Instead, what we're going to do is because we've done that. What we haven't done is cross-examine the data. I haven't had you guys do this yet, so I'm going to walk you guys through this. And what we're going to do here is we're going to figure out, is divergence occurring at 300 millibars? Do we have that divergence happening within our geopotential heights? And are we doing that over an area where we're also getting warm air advection happening at 850 millibars? At 500, do we also have that divergence happening in the same area where we've got 850 millibar warm air advection? Are the wind speeds and direction different at 500 from 850? Is there vorticity happening at 500 millibars in the same place where we've got vertical motion? So do we have a positive vorticity? Do we have energy in the atmosphere in the same place where we've got vertical motion underneath that point? What's our dew point depression looking like at 700 millibars? Is there any kind of vertical motion happening at 700 millibars that's happening in the same place? Again, do we have vertical motion happening over the top of where we're injecting into it some warmer, more humid air? And at 850 millibars, what's our dew point depression looking like compared to 925? So, how do we figure that out? Well, we only need a handful of maps to do all of this. So up at 300 millibars, we're trying to figure out, again, do we have divergence happening? I would argue that yeah, in this area, we've got divergence happening. Your lines are a little bit closer down here than they are here, and again, Memphis is right there. So yeah, we've got divergence happening. And do we have it underneath, or do we have it, and underneath that, do we have warm air advection? I would say yes. We've got wind coming in and around off of the Gulf of Mexico at ahead of this area of low pressure. Again, because wind goes around the area of low pressure like that. So we're pulling in moisture and warm air from the Gulf of Mexico. Okay, so yeah, we do. Is divergence at 500 millibars happening in the same place? So yeah, we've got divergence happening here compared to here. So yeah, we've got divergence happening in the same place. We also have down here some warm air advection going on. And do we have, and again, we can come back up here real quick. Oh, clear that out. Do we have a change in wind direction and speed? Okay, well, we're coming in, and it looks like we've got wind out of the southwest at about, is that 50 to 70 knots? And now it's somewhere between about, this isn't terribly much at all, 25 to 30, let's say. Now, do we have vorticity in the same place at 500 millibars that we have 700 millibar vertical velocity? Well, here's your relative vorticity in here. Yeah, I'd say that we do. I'd say they're lined up pretty close to each other, in fact. That we do, in fact, have vorticity near a vertical velocity. All right, sweet. Yes, we do. We go from 35 knots to 65 knots in the same direction from 850 up to 500 millibars. This is probably backwards. I should have went 65 down to 35. You guys get the idea. The lower levels, the wind is a little bit slower. The upper levels, the wind is a little bit faster. We are going in the same direction. So next up is at the 700 millibar temperature dew point depression, greater than, equal to, or less than, down at 850. And is there some vertical velocity in the same place as advection? Okay, so for that, we got to go to the SKU-T. And again, we're looking here to here, from here to here, your dew point depression. It looks like these lines are closer down here than up here. All right, and then we've got warm air advection happening in the same place that we've got vertical motion. Yes. So yeah, I would say that we are a bigger dew point depression, which means the air is drier at 700 millibars than it is at 850. And there is some vertical motion occurring at 700 millibars on top of where there is warm air advection happening at 850 millibars. So we're pulling air up on top of where we're shoving air in that's warm and humid. This is the start of our conveyor belt. We're moving it in, pulling it up, moving it in, pulling it up. Now down at 850, are we talking about a bigger dew point depression? And from 925, and 925 is like down there, 850 on the line. 925 is about right there. Maybe a little drier 850, but they're about the same. So we've just went in and we've interrogated the data. And so now we have a pretty decent idea about divergence and warm air advection, not only at 300, 500, but we got an idea about is vorticity near vertical velocity. Do we have vertical motion in an area where we're pulling in moisture and heat off of the Gulf of Mexico? Yes. So here's what we're doing. Okay. So we're pulling in stuff off of the Gulf of Mexico into an area at 850 millibars where the air above that point is getting pulled up into a place where there is vorticity happening and energy in the atmosphere. So if I'm an air parcel, I'm riding along and I get to here and now I'm moving up and I'm moving up into an area where there's enough energy at a head of a trough in an area where there's also divergence aloft, which is aiding in the ascension of that air parcel. I'm going to pause on that for a moment. Let everyone digest that. You can run that back and listen to it again if you need to. But the important thing to note here is what we've done by going through all of this is we've basically set the stage that we're pulling in air off the Gulf of Mexico. We're pulling that air up, and we're doing so in an area where there is some sort of energy happening in the atmosphere. We're doing that underneath an area where, if these are isobars coming around an area of low pressure, say I'm an area of low pressure here, and here's our area of interest, we also have divergence happening, and that divergence is opening up the atmosphere for air below it to move in, remember mass balance, to move in and fill that. And so working in 3 dimensions, again here, let me go back to my area low pressure, and we can come around our trough here. At the surface, or in the low levels, at 850 millibars, we've got air coming in from the south to wrap around this area of low pressure. And aloft, we've got wind coming out of the southwest like that. And so we now have a turning of wind with height. We're doing so in an area of divergence. We're doing so in a place where underneath this, in kind of the middle between this point, you've got air that wants to ascend. We've got vertical motion happening. So you've now created a place in the atmosphere where you're moving air that's moist aloft, creating a cloud, probably cooling and condensing it. You're doing so in a place where the wind is probably turning a little bit with height. In this particular case, by the way, remember our wind was actually coming around like this. So we didn't have much of a change in wind direction. So really, ours looked, ooh, that was a weird looking owl. Ours kind of looked like this. The wind came kind of around like that, and then it came kind of around like that. But because of the placement of our ridge of high pressure that was down over here, our wind at 850 was actually coming in kind of like this, while the wind at 500 was coming in. So we didn't have much of a change. And you can kind of see that here, where it's coming in at 850 like this, and then at 500 like that. And not much of a change. But we've done all of this. And cross-examine, we figured all of this out. It's easy to just look at this, but now we know for sure that it's not just bad data in our SKUT, because sometimes you click on this and you can get some bad data. In fact, we can kind of go up here. Let me show you guys an example of some bad data. Here's an example of some bad data. This data is no good down at the surface. Calm wind at the surface in the afternoon in March. Probably not. And that just may be a function of maybe it just sucked in some bad data. And that's for the one point in time and one point in space. You click maybe just over to the left, you click just over to the right, it probably fixes that problem. But we just went through and double checked all of that by going through all of this. All right, on that, we'll take a break. We'll take a break, let you guys get something to drink, something to eat. I'm going to take a swig. All right. I bet you guys wish we had these breaks in regular lecture, didn't you? I don't blame you for that at all. All right. Moving on. All right, back to our deal here, our SKUT here. We've now interrogated our data. We've figured all this out. All right, there's our SKUT. Now what we need to do, now that we've figured all this out, we can go back here. And remember that we said that we were with convergence on the northwest flow, peak of the ridge, okay, southwest flow, and then mesoscale lift, precipitation possible with the right ingredients. Well, we have all of those ingredients. Now we got to take, now that we know that we've got the ingredients for precipitation underneath that mesoscale lift, because we're trying to figure out the specific forecast for March 28th, we got to go one step further. Values worth noting for severe weather. And to get that, I blew it up on here so you guys could see the numbers a little bit easier. But you guys know where to grab these on the SKUT. We were just talking about that a couple of seconds ago. It's all this stuff, it's kind of hidden back in behind it now. But I blew this up. So, ML cape greater than 600, check. PWatt greater than 1.5, check. Downdraft cape greater than 500. No, we're only at 400. But remember, these aren't hard-cut thing. Nothing in weather is hard-cut. It's not black and white. We're always shades of gray. So we're at 400. Kind of close. Lapse rate is 6.5. Close. The surface is 6.6, but the rest of them, close. Shear values of 40 knots are greater through the column. Down to the surface to 1 kilometer, we don't really worry about that. But surface to 3K and surface to 6K are the most important ones. And yeah, I'd say we have that. Helicity up over 150, surface to 3 kilometer. And here, let me highlight where I'm looking. So here's the mixed layer cape, right in here. Oh, hold on. Here's the mixed layer cape right in here, right? And then it's that number right there. Just in case you guys forgot during spring break, there's your P-watt value. There's that number right there. Your downdraft cape is right there. That's 411. Right there. Your shear values are going to be right here. And we're looking at surface to 3 kilometer and surface to 6 kilometer. Your helicity values are right here. And that's what we're looking for there. Next up on the list is SCP. That's the supercell composite value right there. And your STP, which is right below it. We were looking for values of 5 and 2, or 2.5 and 0.5. Or the fixed layer. Sorry, we should probably go fixed layer here. Of 0.8. So no, we didn't hit those. K-index of 35. K-index is right there. Oop, right there. 36. Bingo, got it. Total is 50. We're not greater than 50, but we're right on the nose. And our ML-LCL heights, mixed layer, LCL. So we just follow the matrix, and we're looking right there. LCL heights. Yep. So we got that one. And then most important on here, can we convect? Will we even get convection? Is our max temperature higher than our convective temperature? Yes. Yes, it is. So we will have convection. All right, sweet. So we knocked a handful of those off, right? We did pretty good. Some of these values worth noting. So what have we figured out? Okay, we go back to here. On the 25th, a mostly sunny day, we're underneath an area of convergence with a northwest flow. We kind of nailed that one. We did pretty good on that one. And remember, all we did for that was look at the 500 millibar wind. March 26th, we're peak of the ridge. Again, the clouds are maybe starting to increase. All right, southwest flow begins on the 27th. We have synoptic scale lift, maybe a couple of extra clouds in there. However, we probably don't have convection because our max temperature was not higher than our convective temperature. So it does get very difficult to get convection to happen. Then on March 28th, we were close to saturation from the surface up to 500 millibars. Our surface dew point was near 70. That's chock full of moisture. How about I spell? It's neat too. Dew points are neat, but they're near. Mid-level vertical motion, we had that. Remember, we checked that off the list. We got 8 of those 11 severe weather parameters of our values worth noting off the list. So storms, yeah, I think that's probably a safe bet that we end up with thunderstorms. That's probably a safe bet. And what maps did we use? 500 millibar wind, 500 millibar vorticity, vertical motion at 700 millibars, 850 millibar temp, and we used our skew T's and we pulled some data off of those. So for your assignments, you're going to have access to way more data. So these forecasts for you guys should be a breeze. And keep in mind, we didn't do anything in here outside of all of the stuff that we went over in class. All we did was apply a lot of the things that we've learned in lecture. I didn't use any extra information or smarts or anything more, a different textbook, nothing. All it was stuff pulled directly from lecture. All right. Now, how do you find the data for your forecasting assignment? A great question. And I tell you, it feels like a bug is stuck to my nose. I can see it. It'll pass in front of my glasses. It's like this little gnat or something. I think it keeps bouncing into my nose. Drinking too much soda lately. That's why I'm switching to water. All right, so we got to pick a random U.S. city, and I went to randomuscity dot whatever this is to figure this out. And so we're going to hit this a handful of times while I'm talking, and this just kicks out random cities, and then we're just going to pick a random city that seems like a lot of fun to do a weather forecast for. Of course, that one was Memphis. That was on the original list. And how about we can I can click it a handful of times and stop here. How about this? Do any of these look like fun? Absolutely none of these look like they would be any fun. I guess we can do Indianapolis. How about that? We'll do Indy. We'll do a forecast for Indy. So what you'll do is you'll go to pivotalweather.com. So if I was like, hey, forecast for Indianapolis for, let's say, I don't know, a couple of days from now. All right, I'm recording this in late March, so we'll say April 5th. All right, so you're going to come to Pivotal Weather, and it's going to look. You're going to go pivotalweather.com, and you're going to come to a screen that looks like this. You want model data, and the model data that you want will pop open in front of you. Now, what we're going to use here is the GFS, and we're going to use the latest rendering of the GFS, and you can find that in the drop-down menu on the left-hand side. And again, like I said, we're recording these. I'm recording this one in specifics during spring break, so you can see that we've got a whole slew of different ones that we can look at here. And then your forecast hours are right here, and these are forecast hours looking into the future, all of 384 hours. You can go forward one by clicking here. Or what you can do is you can go over here and you can make it, instead of a single image, a forecast loop. Then, using the caret keys, or the period and comma key, you can go forward in time, backward in time, forward in time, backward in time. Our forecast for Indianapolis, I said, April 5th. Let's see how far out we can go. Can we get to April 5th? We can. Here's April 5th at 18Z. So what we'll do is we'll take a look at Indianapolis, or it's kind of close to it, for April 5th, which is 330-something hours away, or 36 hours away. So I'll come back over here, and I'm just going to find 336 hours, and I'm going to click on that, which gives me April 5th at 18Z. You can see that right there. And what do I want to know? Well, I got to figure out what the weather forecast is. So, first things first, I'm going to go to the 500 millibar wind. How about this? Here's an interesting map. Let's kind of scroll down a little bit for you guys. How in the heck did we get here? This is interesting. So, what we've got is wind. Let me turn my deal back on here. Coming around and down around an area of low pressure, wrapping back around to the north and west, and then back around a ridge, and then into another trough. Now, this is not a likely scenario, so we're not going to use this. I made up a date, but I'm changing my mind. Let's go back in time. How about, sure, this looks like fun. What'd I click on? 162 hours. So this one, way more fun than the one that we were just looking at, and way more accurate. All right, so this is the 29th at 12Z. Let's go forward in time a little bit. Let's do 18Z. Let's get into the afternoon. So there's Indianapolis. We're right next to, up at 500 millibars, our area of low pressure. And we've got divergence happening. You can see that happening in our area. We can click on our sounding here for the time that we're concerned about. And you can see that even though we're close to that area of low pressure, we're not really fully cloudy, are we? Interesting. So let's digest and figure out what's going on. So that's up at 500 millibars. There's your wind. It's going pretty quick. We can come back down to 700. Let's look at the vorticity. Let's see what's going on with vorticity here. And you can see we've got a fair amount of energy in the atmosphere here. We just may be lacking some vertical motion, perhaps. Yeah, well, no, we got vertical motion in here as well. Are we lacking some low level? So let's go back up to moisture here. And I'm going to go to the 850 millibar dew point. Are we lacking low level moisture? That's our problem. So here's Indianapolis. We've got a dew point of just 2 degrees because our wind at 850, we're so close to the area of low pressure that we're actually pulling wind around from the backside of the area of low pressure, and all of the moisture here is out ahead of the area of low pressure. So in Indianapolis right here, give or take, there's no moisture left. So the reason when we clicked on that sounding and we said, well, wait a second, we're really close to the area of low pressure. We've got some omega in here. We've got a lot of wind. We don't really have much in the way of severe weather parameters, but given how far north we're looking, the parameters that we usually use for class are probably not going to be as useful. But nevertheless, this explains why it's so dry. It's dry. We're on the back side of this area of low pressure. So when we go back here and we say, well, yeah, we've got vorticity happening at 500 millibars. Sorry, there we go. And we've got vertical motion happening. Well, vertical motion is all fine and dandy, but if the air that you're moving vertically is 850 millibar dew point, dry, so it's got let's say a 3 degree dew point, and you lift that to 700 millibars where you've got even more vertical motion happening, well, you dry out the air as you move up. And so because the air is also drying as you move up, even though you're pulling some of that air in, it's not moist enough to start to worry about creating clouds and showers and thunderstorms. As a matter of fact, what we can do is we can go down to the surface and we can see, is there any precipitation? And the answer is not really. We may have missed out on it by just a little bit. And again, this is why point and click forecasts aren't great. If we were to go back in time, you would say, oh, well, maybe there is a chance for rain, because if we go back in time, look at that. Now we're fully moist down at the surface, but when we went forward in time, we dried things out pretty quickly. Is there a chance as we go past this point that rain gets back into the area? Yeah, look at that. So what we did is we found the one point in time where we had gotten, in essence, what we call in the weather world, dry slotted. So if we go back ahead and back even further, and back even further, you can see that the forecast should include clearing skies because we were moist and raining, and then all of a sudden we weren't. So if we just picked this is, by coincidence, a great example of when point-and-click forecasts can fail you. If all we did was look at this one point, we would say, well, yeah, sure, it's a dry day, despite the fact that we're near the area of low pressure. But if we go back in time, you can see that the rain was close, and eventually it will rain again before finally clearing out. So our 18Z time, 6Z, 12Z, 18Z, 18Z was kind of the only time where it wasn't raining. Pretty incredible. You can see, actually, if we go back to the previous day, and we were to click on the sounding here, yeah, fair amount of rain. Also, right along the warm front, or at least very close to it, given the wind profile. If we go ahead in time one more, my guess would be we're pulling wind out of the east and kind of east-southeast at this point. Then eventually, we flip back around to the northeast as the front kind of sags back to the south. Once the area of low pressure swings by, now we've got wind out of the southeast. One last gasp of rain. Now we're out of the southwest. Dry slot. And then back in behind that, wind out of the northwest as we cloud things back up. So again, another example of just a quick forecast. And hopefully a good example of an easy place to find the data. Also, just as a note, all this stuff on the left-hand side, these are all your parameters that you can look at. You've got your different heights in the atmosphere and wind, your different heights in the atmosphere and temperature. You just click on this next one. Here's all of your surface information, your precipitation, how much rain you're going to see, upper air moisture. I clicked through this stuff kind of quick, so I thought I'd take 5 seconds and walk you guys through this. Your relative humidity at different levels, your dew point at different levels, dynamics, here's your vorticity at different levels, your velocity, vertical motion at different levels. Here's some of your severe weather parameters, and we won't really worry about this, but if you ever get curious, you can look at winter weather stuff. So that is a look at creating a forecast. We did 2 of them. The second one was kind of quick. It was basically just helping you guys walk through looking at some of the data. But hopefully it helps you understand why point-and-click data doesn't always work, just by happenstance that happened to work out pretty well. But why point-and-click data doesn't necessarily work, and how you have to look at previous hours and sometimes even following hours to figure out what the forecast for a specific point is actually going to be at a certain time, because sometimes that point-and-click data can let you down. So again, this was the last official lecture for you guys. I suppose I'll probably have another couple videos out for you guys, letting you guys, walking you through some stuff, answering a couple questions, etc., helping you guys out with some of the homework assignments, the forecasting assignments. But prepare for the final. Probably have another video for the final as well. But as you guys continue to prepare for the final and continue to do your forecasting assignments, feel free to shoot me an email, ask any questions you have. I'm always here to help.